Okay, is there one from the written that you want to talk about? What you're handing in now? Is there one of those you want to talk about? So you got them all? Okay, I do want to look at number 11 from your My Math Lab. Okay, here's number 11. I want to talk about this one. So right here, this expression, p prime of t equals 10 e to the minus 3t. What's that about? So when you look at that, what do you think? What do you see? What does it mean? Adelaide? She's saying this is the rate of change function. Agreed? Okay. And then what about this piece of information here? Okay, so it's the value of what at 0? Accumulation, right? So it's the value of the accumulation when t equals 0, which is 100. Okay, so they want us to, and what do they want us to find? If they want us to find p of t, what is it they want us to find? They want us to find the accumulation function. How many accumulation functions are associated with this rate? One? Many. So how are we going to find the accumulation function associated with this rate? If there are many. DJ?
We're first going to find the accumulation function, then we're going to plug the values of when p equals 0, accumulation of 100 back into it.
So of all the accumulation functions associated with this rate, does this pinpoint the one that we want? Is that what we're saying? Yeah, that's exactly right. So given this information, we have this one point of at 0, we have 100 of accumulation. That pinpoints the one of the many accumulation functions, right? So how can we get the family of accumulation functions? So what should I write here that gets us started? Adonijah.
Sorry, what's the question?
Okay, so what can I write to get us started? If this is the rate function and I want to write all the accumulation functions, how can I do that?
You can do the antiderivative and then throw on an arbitrary constant.
So, but I want to express this first. How can I express this before doing any work? How can I express all accumulation functions associated with this rate? Autumn.
That would be like the integral of 10e to the negative 3t dt.
So without bounds there, remember without bounds, what does it mean? It means all accumulation functions associated with this rate. Okay? And so then, from there, if we want an accumulation function from the rate, then what am I going to do to find that? Stanley.
We know you've got e to the something in the derivative, so the original function must have also had e to that same something.
So what I heard you say is that this is the derivative of some function that we're trying to find.
Right.
Is that right? Okay, so in general, let's just make a stab at it here. So if we got 10e to the minus 3t, what's a general guess at the function whose derivative is this?
Well, that's that e to the negative 3t.
E to the negative 3t. What about the 10?
Well, after you take the derivative of the e part, you're going to have to multiply it by a -3.
Let's do that later. What about the 10?
Well, whatever. I know what it has to be, but I don't know.
No, you're trying to do it all. I'm just asking about the 10. What happens to the 10 when we do this antiderivative?
It's not going to be the same in the original function.
No, you're still trying to do that. I'm just asking about the 10. What happens to the 10 when you do antiderivative?
It's hold on.
Yeah, it just stays. Okay? So when you take the derivative of something times a constant, the constant just comes along for the ride. So for the antiderivative, same thing. Okay, so, and then how do we show that it's all antiderivatives? No, we're not done yet, but how do we show all antiderivatives? Plus C. Okay, cool. All right, now, is it right? How can we figure out if it's right or not? Take the derivative, okay? This is a requirement whenever you're doing antiderivatives, especially harder ones, which we're going to get to later, especially with harder ones. When you have your first attempt or you think you have it, take the derivative and compare it. So what's the derivative of this? Dan?
-30 e to the -3t.
Okay, agree with that? Okay, so is this what we started with? Different by? So all we got to do now is adjust this first attempt, so that when we take the derivative of it, the -3 is not there. Chunzi, how can I adjust this so when I take the derivative, the -3 is not there, and it would be this? Divide by -3. What do you think? If I divide this by -3. Yeah, that's it. So now when I take the derivative of it, that won't be there, and we'll have exactly what we wanted. Okay, so we've got all antiderivatives that have this rate, but to find the one that we want means finding that value of C using this, right? So C is 100, right?
No.
Okay, well, thousands of calculus students throughout the ages have tried to say, oh, well, if it's at 0, it's 100, then C is 100. But we're going to find out that that's not true, so we have to work it out.
So it should be 10e to the -3t over 3 plus c equals 100.
Equals 100. Okay, so the output is 100 when t is 0. So C is 100 plus? That's 1, right? 10/3. So now we got it. So with that piece of information, so -10/3 e to the -3t plus 100 plus 10/3. Whatever that is. Okay, does it make sense? So when you're doing problems like this that are just kind of symbols and algebra, keep asking yourself all those questions that I'm asking you. What is the meaning of this expression? What is the meaning of this expression? Okay, keep practicing that, because that's the real, that's really the meat of it. So you could train anyone to move symbols around and plug numbers in and crank out values. But there's meaning behind the whole thing, so keep practicing that. And you know that's what I'm going to test you on, right? That you know that I'm going to be testing you on the meaning, not just do you know the procedure. Okay, any questions on this one? Makes sense. Okay. So let's just talk about, you have your third exam this Thursday. So briefly. If you go to on Blackboard, if you go to quizzes and exams on Blackboard and click on exam 3 and related quizzes, the review outline is up. We'll show you that in a second. And then I started getting all the blank versions and solutions of all the quizzes that apply to this this exam, which is actually 7, okay? There's actually 7. But some of these are like half quizzes, right? So there's a few that are like 1-pagers, okay? So it's not, average length of the quiz is 2 pages. So, and the other thing is we had the mastery exam, so it's been a long time since exam 2, okay? So anyway, I got the blank versions, and then solution versions, and then by the end of the day I'll have the remaining 3 up, okay? How do you study? Don't print out the solutions and just sit there passively staring at the solutions. What I suggest is go back to the blank version and work it as best you can, and then do research, figure out what you're not getting, and in the very end, very last resort, then take a look at the solutions and think through what's going on there. Okay? So study in an active way. Don't just take the solutions and read them and say, oh, I get what he's doing, and then move on. Because that you probably don't. Okay? So you got to put yourself in that kind of the testing situation. Okay? The review outline, here it is. It's because it's covered such a long span of time, I've tried to point out here on the topics I've pointed out the dates of class that are the most important. So I've kind of tried to cut it down in terms of, so not every date is mentioned here. Okay? So it's basically through February 27th through last Monday. Okay? Optimization is the last thing. Okay, so all this stuff, since we did optimization, the fundamental theorem, and antiderivatives, very, very important for the final, okay, but won't be on this exam. So you got rate from accumulation, deriving the derivative rules, graphs and implicit differentiation, related rates, inferring accumulation from the derivatives, and optimization. And so I won't read through all the bullet points, but there's nothing on the exam that's not represented somewhere on this review sheet. Okay? Everything on the exam is represented on this review sheet, and I've tried to hone you in on the days of class that are important. Any questions on your exam, which is Thursday, exam 3? If you haven't started studying, do not wait till Wednesday night. Okay? There's lots here, so get going tonight and set aside time every night, and then bring your questions to me Wednesday or Thursday morning or whenever you can get with me so that we can have a conversation, right? So it's in those conversations, after you dug in yourself, you bring your questions and we talk, and we fill in the gaps, and we make sure that you really understand it. Okay, questions about exam 3? Okay, so we're talking about the fundamental theorem. So do you remember what the fundamental theorem is? We've been doing it all semester, so it's really not anything new, but we need a formal statement of it. Do you remember what it is? What it has to do with? Anyone? What's one part of it? What is it? Anything. You offer anything up. Marcus. You're just reading what you wrote down last time. I'm going to see if anyone remembers. Daniel, do you remember?
Maybe the integral from a to x of r of x
Okay.
equal to f of x.
Okay. Yeah. All right. So, no, he's not looking at this. All right, so it's all about what the open form accumulation, exact accumulation function equals, right? That's what the fundamental theorem is about, is saying we've got this open form accumulation function. Can we write it in closed form? That's what the fundamental theorem is all about, and we've done all the math up till now to say, yes, this is how we can write that open form accumulation in closed form. We just need the antiderivative of the rate function. We need the antiderivative, any antiderivative of the rate function. Okay? And then if we plug a value in, then we're actually finding a net change of accumulation. This is the net change, right? So let's write that down. That's important. So when you use the accumulation function, you're calculating a net change of accumulation? How much weight of sand had accumulated between 2 seconds and 3.5 seconds? Remember that question? We represented it as an integral, the process of adding up bit by bit the weights of sand, and we represented it as the accumulation up to 3.5 seconds minus the accumulation up to 2 seconds using our accumulation function. That's what the fundamental theorem is all about. Okay, so let's test it. All right, so we're going to use graphing calculator. We're going to look at the accumulation from 2 to 5, given a certain rate function. We're going to look at the accumulation from 2 to 5, and we're going to have graphing calculator calculate the open form version, and then we're going to use the antiderivative and check the closed form version. Okay, this should go pretty fast. So. So not even graphing, we're just going to there we go, perfect. Okay. So what's in the first case, our rate is cosine 2x. Okay? So I got the integral from 2 to 5 set up here, and it tells me what the open form accumulation from 2 to 5 for a function having this rate is. And it's took it to 4 decimal places. Okay, so now we're going to compare that. Now we're going to use the fundamental theorem to see if we can get that same value. So the first thing we need is the closed form antiderivative. This, Daniel. How about cosine of 2x? Can you do that closed form antiderivative? Sine 2x. So how can you check? So you're not sure, so how can you check? And what would you get? Almost. What's the derivative of sine? Is it cosine, okay. 2 times cosine 2x. Is that what we have? So adjust it. See? So it's all about taking a stab, taking the derivative, and adjusting. He did it all himself. I just had to ask the right questions, right? Okay? So now, we want to put that in. You're going to put that in the graphing calculator, and then we can have a line just calculating. So, is this the only antiderivative? Okay, so I want to do this. I want to add e to the pi. Still okay? I added e to the pi. Yes. Yeah, because what's the derivative of this? Cosine 2x. Still an antiderivative. Still an antiderivative. Okay? So you can make up your own. So what's another antiderivative? Connor.
Of cos 2x?
Yeah.
1/2 sine 2x plus 6.
1/2 sine 2x plus 6. What do you think? Yeah. Okay. So make up your own, right? There's a lot to choose from. So now I'm going to put in our antiderivative here, which is 1/2 sine 2x plus e to the pi. All right, and then we look at, so now we've got that antiderivative. We evaluate it at 5, evaluate it at 2, and subtract. What do we get? Works. Okay, so what I'll have you do is you do these 4 boxes, and then we'll come back and check the open form later. Check it with the open form later. So you do these 4 boxes, You'll need some kind of, if you don't have graphing calculator with you, you can use a handheld, or you can use graphing calculator. You do these 4, and then we'll check them against the open form. Once you come up with your antiderivative one more time, how can you see if it's right? Just take the derivative. And if it's not right, that helps you to see how you need to adjust your first guess. Okay? So try to stay focused on the task. I'm going to hand quizzes back. And look at these later. Chenru. David Lee. C. Lee. Okay, try to stay. Try to look at these later, okay? Try to look at these later. Stay focused on the task at hand. DJ.
So you're saying
So the second part is plus 1/2.
And the rest of it. Sounds like there's some good conversation.
Negative 2/3. Oh, it should be negative 3/2. It should be. Wait, no. At 3x. X to the negative 2 plus x.
Keep winning.
So for what we're supposed to add here,
It's 3.3.
Okay. Closed form. Let's see. Lauren, what would you get for closed form for e to the minus x plus x? E to the minus x plus 1/2 x squared. So let's take the derivative of it. What's the derivative of e to the minus x? Is it just e to the minus x? Yeah, but we got chain rule, right? So how would you adjust it? That's it. Minus e to the minus x plus 1/2 x squared, and let's do something more interesting here. So what's a different one? Give me another one. So this is one accumulation function. Give me a different one that's more interesting. Okay? Marcus.
Negative e to the negative x plus 1/2 x squared plus 500.
500. Perfect. Make sense? Okay. So, what happens when you put that in? So we have minus e to the minus x. It's minus e to the minus x plus x squared divided by 2 plus 500. I got 10.6286. Anybody else?
Yep.
Do we trust that?
Yes.
Yeah. If we double check our work, right? But what do we trust more? Open form, right? Open form. So we're going to put in e to the minus x plus x for the rate. There it is. 10.6286. Now we trust it. Okay, so now we trust the work we did because the open form accumulation from 2 to 5 is the same. All right, Corey, tell me. Closed form.
I believe it is 3 ln x plus x.
3 ln x plus x.
Yes.
Let's spice it up a little bit.
Plus 4 pi squared.
4 pi squared. What do you think? Did he find a closed form antiderivative for 3 over x plus 1? He did. I got 5.748. Someone else? 7.4. We'll just say call it 7.49. All right, check it. We're just going to put that original rate function in and let graphing calculator calculate the open form. Same. So why is this powerful? Why is this helpful? Okay, because we need a machine to do that. And we have a machine to do that, but with our knowledge of derivative and antiderivative, we can do it in a more direct form or closed form based on functions that we know. So it's kind of like a fast track for what this represents. This represents that process of adding a zillion little bits together from A to X, from 2 to 5. And so this is just a quick streamline calculation that gives us that same result as the accumulation bit by bit from 2 to 5. Okay? Any questions on that? Okay, so there's this notation that helps write this a little more compactly, and we'll see this and we'll use this. So make a note of this. that when you're taking a function and plugging in two values and subtracting, which is what we do with this closed form accumulation to get the net change, okay? We have this here. We just write the function once, and then we put a straight bar, and then we write this is called the lower limit, and then the upper limit. And that's an alternative way to write this exact same thing. So this expression right there means exactly this. It's just a way of writing it so we can just write the function once. So like if this is a long function, right? If this is like a long polynomial or something complicated, then we can just write it once and say, and this will mean to plug in each value and subtract. Okay, so be on the lookout for that. That's what that means. Any questions? Okay, so let's put it all together here and do an example. So it's similar to one we've had before, or it is, but we're going to kind of use this example to put it all together. So the rate of change of elevation with respect to distance and feet of elevation per mile of highway for a stretch of Colorado highway going east of the Utah border is, here's the rate. So what was this? What were the units on this again? This was feet of elevation per 100 feet of road. So this is feet of elevation up and down per 100 feet of road, where x is, this is not right. Well, it doesn't matter whether it's per mile or per 100 feet. We understand what's going on. So where x is the number of miles, from the border. Okay, so in that case, I guess it does need to be this does need to be miles from the border. Okay, so feet of elevation per mile down the road, where x is how many miles we are from the border. Okay, so here's a graph of, this is our miles from the border. And this is elevation in feet. Is this r of x? Is this r of x? Some up here are saying no. What do you think? More people are saying no. All right, so you think it's not the rate of change, okay? So let's ask the question, what is the accumulated change in elevation from mile 2 to mile 5? Before we do that, let's represent this. How would this change of elevation be represented on the graph shown and using the rate function given? Okay, so you take a moment, you can do it with the person next to you. We want to represent that change in elevation on the graph. We want to represent that change in elevation using the rate function. Go.
Elevation. Is elevation. Or A.
So we're just representing it now. right now. So representing on the graph, representing it with the rate. So no, we're not calculating anything. Just how would you represent it? Okay, so let's see. Richard, how'd it go? Take your pick. Can you get either one of those? How would you either represent it on this graph or represent that change in elevation using the rate function? Integral of the rate. So using the rate function, you want, so be more specific. So integral of do I need anything more here? Okay, dx. Or yeah, if we want to do t, we could put t's in, that's fine. Anything else? So from 2 to 5. Yeah. Okay, did you get that? So when we're not writing it as a function but as a net change, we can use x here, it's fine. You can use x, t, whatever you want. And then if you use x, then x is representing tracking the little changes from 2 to 5. But when we have a function like 2 to x, that's when x is going to mean the last value, and we need a different variable to track the little changes along the way. Okay? But if you've got from 2 to 5 like this, any variable is fine. Okay? What about represent this on the graph? Talia?
So the y value at on the miles of 5.
Y value miles of 5. Okay.
Y value of miles of 2.
See if I can get this straight. Okay, and then y value at 2. And what do you want to do with those?
Subtract from that 5.
Subtract this y value, or this y value from this one. Would that be a representation of the change in elevation from 2 to 5 miles from the border? Yeah. Okay, so let's just estimate that. Looking at the graph here, what would you estimate?
475.
Yeah, I kind of went down a little bit too much. So let's say, can we say 480? Okay, 480, and then
300.
a little bit below, maybe 295. Not quite 300. All right, so based on those estimates of those elevations, what's the estimated change or net accumulation?
185.
How much is that? 185. No, I don't think so. What are we going to do with these two numbers? Subtract. So we're going to have 480 minus 295. Tell me.
185.
It is?
Yes.
Okay. Sorry. 185 feet. Okay, sorry about that. All right. Are we good? So now we want to use calculus to see how close our estimate is and get something more exact and check it against our estimate. Okay, so here's that rate function. Here's the first way of representing it, from 2 to 5 of the rate dx. How are we going to use this? How are we going to check our estimate of 185? What are we going to do? DJ.
Plug it in the graph calculator.
Okay, how can we use the fundamental theorem to do it? Yeah, that would be absolutely right. We could plug that into graphing calculator and it would give us that accumulation of height from 2 to 5. But what about using calculus? Okay, need an antiderivative? So, can we do the antiderivative? What about the 52.8?
States.
Stays. So we'll just do that. Antiderivative. Okay? Antiderivative of cosine x e to the sine x. Can you see it? It's just going to be e to the sine x. Because its derivative is e to the sine x, cosine x. There it is. Okay?
Plus 2x.
Plus 2x.
Plus c.
Plus c. Okay? From? Actually, let me write that down here.
So at this point, we can find a change in elevation, but we can't find the original.
We can't find what?
We can find the change in elevation from 2 to 5 miles.
Okay.
We can't find the original position function because we're not given the c.
Okay. All right. So that kind of leads me to my next question. No, that's good. No, it's a great question. Excellent. Do you hear what he's saying? He's saying we can find this net change, but what about the actual just the function of accumulation? So let me go back. Okay, so how does this relate? So how does this relate to the overall situation? What's that? Or maybe just this much. So just the function.
The curve itself.
He's saying this function is this curve.
Yeah, leave it.
Not
The long.
necessarily its elevation, but just if you add a c, it changes the elevation.
Okay, if we had the right value of c,
Just move it up or down.
if we had the right value of c, would it be this curve? Yeah, this is our accumulation function. All right, or it's all of them, but we know there's one, and that associates with one value of c that would give us this graph. And how would we find c if we wanted to?
We have an ordered pair.
What order pair do we have? 0, 0. Okay, so if we use the 0.00, we could nail down what that value of c was, and we'd have the actual accumulation function. All right, but we just want to go ahead.
I don't know if I'm like playing devil's advocate. How did we know it was 0, 0?
Um,
Was it given to us?
Wasn't precisely given, but I assumed from the graph. I made an assumption that it was, yeah. Okay, so now so here's this notation, right? The function with the bar and the 5 and the 2. What does it mean?
Plug in 5.
Plug in 5,
Minus plug in 2.
plug in 2, and subtract. Okay, do it and see what you get.
Plug in 5, plug in 2. Do it again.
So I'm going to use graphing calculator.
We had that file. Yeah.
Look, I'll even, in graphing calculator, I'll even write plus c. Okay, how about our prediction? Are we in the ballpark?
Yeah.
So you see right here, here's our accumulation function, which was the antiderivative of the rate. You guys okay? You have a question? So here's our antiderivative of the rate that we found, and then evaluated at 5, evaluated at 2, the difference, about 206 feet. And what did we guess? 185? So 20 feet off. 20 feet off. And that was, my lines weren't straight. Okay, So does that whole process make sense? So that's bringing everything together. Fundamental theorem, rate, accumulation, really important example there. Okay, this is just going over what we did. There's our antiderivative. Just use C equals, you could do C equals anything when you're actually evaluating at two different values. There it is. Okay. Really important example because it uses the fundamental theorem and brings together all these ideas. Anybody have a question? Give you a second to think. So it should feel like really not anything that's too much new because we've been working up to this the whole semester. We've been talking about this the whole semester, building it up piece by piece. So we had all the pieces. So this should feel like review. Okay, so let's look at some. These kind of expressions are a nice way to test our understanding of all the symbols. Okay, and by giving more complex expression. So I want to make sense of this. Okay, so making sense of it does not mean reading it from right to left. So I'll read it from right to left. It's the derivative with respect to x of the integral from 4 to 7 of sine of 3 cosine x dx. It's exactly what that is. So what I said is perfectly accurate. But it doesn't. What I said doesn't really reflect any of the meaning of it, and that's what we're after. Okay, so again, it's the derivative with respect to x of the integral from 4 to 7 of sine of 3 cosine x dx. So now I want you to take a moment to talk about the meaning of that. So what is the meaning of that? Go, talk to somebody. Okay, Richard and Daniel talk. Daniel and Chelsea talk. Olivia and David talk. Lauren and Owen talk.
Oh, it's going to become rate. What?
Well, it does. Your boundary here. I'll just
Okay, let's regroup. So, Stephanie, just tell me one thing. So, in terms of meaning of what's going on here, can you just tell me one thing? Derivative of the function? So it's the rate of change. So you're saying that it's this is saying the rate of change of this whole thing. Okay? Jacob, you agree with that?
Yes.
Tell me something else.
It's from 4 to 7.
Okay. What from 4 to 7?
The rate of change, it's asking for the rate of change from 4 to 7.
It's not the rate of change from 4 to 7. Megan. The rate of change of the accumulation from 4 to 7. What do you think? Okay. Is there more to say here? Is there more to say? Chelsea. Dan, is there more to say? So the rate of change of the accumulation from 4 to 7. What's that?
Is it the rate of change of the rate of change between 4 and 7?
It's the rate of change of the rate of change. Beth, tell me. It's the rate of change of the accumulation from 4 to 7. What's that? What's that?
The rate of change of the sine of 3 cosine.
Yeah, so that thing is accumulating at a rate of this, sine of 3 cosine x. All right, so now let's try to answer what it's asking for. So now we've got this rate of change, and we're accumulating from 4 to 7. And we take the rate of change of that accumulation, right? So what is that? Tyler. Sine of 3 cosine x. What do we think? Agree? Adonijah, agree?
That's the function, is that what we're doing?
Yeah.
Daniel.
Maybe looking at this completely wrong, but I thought it was 0.
He thinks it's 0. Why do you think it's 0?
So you take the integral from 4 to 7, or you find the accumulation from 4 to 7.
Accumulation from 4 to 7.
That's just a number.
That's just a number.
You take the derivative of the number, you get 0.
He's saying you take a derivative of a constant.
Yeah, but I think that's all. I bet it's
He's right. The accumulation from 4 to 7 is a constant, and we're taking the rate of change of that constant. Yeah.
But if it was like an open form, and there was no
Like this? Okay, now how about this one?
that'd still be.
So now this is the rate of change of the accumulation from
4 to x.
4 and so
So 4 would give you a number.
is that a number?
No.
Yeah.
No.
No, that's a function, right? That's a function of how far you accumulate to. It's a function of how far you accumulate to. Okay? So, how can we make sense of this? So what does that equal? So this is some rate, right? Which has some antiderivative. Just call it f of t, okay? So f of t is the antiderivative of little f. So what does this equal if capital F is the antiderivative? Sharon. So d dx of what? Big F of x, right? It's the antiderivative.
Big F is x minus big F.
Right. Okay? And what's that?
Big F. The accumulation.
So, this is the antiderivative of little f. So what is its rate of change? What is the rate of change of the antiderivative of little f? Right? This is the rate at which that one's changing. It's its derivative. So what is this?
Sine of 3.
That's right. Sine of 3 cosine x. And what's this? 0. Okay, so this is sine of 3 cosine x. Okay, so just a warning. Just because it's a function and we're taking the rate of change of the accumulation function, you can't just write this down every time. Okay, this is your warning. You've got to work through this process because there are other examples. You work through this process. You can't just write down that rate that's inside. Okay, so this process is critically important. Keep analyzing meanings of every expression. Okay, so you got my math lab for Wednesday. Okay, and then your exam Thursday.
What was one of the problems I had trouble with in my math lab?
Sure.